Okay, so here's another interesting problem. We're doing volume based off of the slicing technique, and we look at cross-sectional areas. So in this problem, it says we're going to compute the exact value in terms of pi of the volume of the object given that here's the key, the cross-section perpendicular to the base, going to be semicircles. So we have to go back and think about what is the area of a circle. So area of a circle, everyone knows, say it with me, is pi r squared. So for a semicircle, or half of a circle, it's going to be pi r squared over 2. Now, we can split this up, and I think the easier part is if we did split this up again and treated this as, this is one part where this is our radius. And this, by the way, is the radius as well. But the radius of this big block, this bigger part that goes from 1 to 5, this radius is a constant radius. And if you notice, it's going from, how far is that? That is going to be 0 to 4, so it's 4. So here's our center, our axis of rotation. And then we have radius equals 4. That. So think of this as it's a semicircle. That was not a very good drawing. Let's do that again. So imagine this, that's our semicircle that's going to be rotated over there. And that's just for this one big part here from 1 to 4. 1 to 5, I should say. So that's a distance of 4. Now, so the volume for that part is going to be the cross-sectional area times the length, I guess, if you want to call it the length, because the cross-sectional area is the height. So what we're looking at is, with a radius of 4, that's going to be pi times 4 squared divided by 2 times 4. That's going to be, I can reduce the 2 and the 4 here. Pi times 16 times 2, or 32 pi. So that's for this part here. That's that part. So now we want to look at this first part. And I'm going to scroll up a little bit here. And the first part we have is, it's essentially, it's a triangle. But if we think about this along the axis, it's this triangle that then is rotated. It's rotated. So it's kind of like it's like a point again. It's narrowing down to that point, and it's curved here. So just think about that shape, and it's not too hard to come up with what this radius is going to be. It's basically how far is it from the axis to the line up here. And if we just see the equation of the line, it's going from 0 to 4, has a rise of 4 and a run of 1. So our radius is going to be 4x. It's just the equation of the line, and that's going to give us the height. So when we look at volume, it's going to be the pi r squared times the length, because I'm calling this the length here. So our cross-sectional area times the length, and that's going to be pi times 4x quantity squared, oh I forgot, divided by 2 because it's a semicircle, times our length, and our length is the dx. So we're going to end up with that pi times 16x squared divided by 2 times the length, or pi times 8x squared times the length. So I end up with this formula, and it's going to go from 0 to 1, because we're looking at 0 here to 1 there, of 8 pi x squared dx. The dx is representing this variable distance from 0 to 1. That's going to give us 8 pi x cubed over 3 from 0 to 1, And so we end up with 8 pi over 3 times 1 minus 0, just that's 1, so it's 8 pi x cubed. 8 pi over 3, excuse me, no x cubed anymore. So we have the two parts together, 8 pi over 3 plus 32 pi from the other part. I don't know why I wrote it over 2, 32 pi. And the common denominator, let me just confirm that was 32 pi. Yeah, there it is. So the common denominator is going to be 3, so multiply by 3 over 3. And we have 8 pi over 3 plus 96 pi over 3. 896 is 104 pi over 3. And that's it.